Welcome to the lecture 3 on renewable energy sources and applications. Myself Dr. Saradindu Panda. Today I will discuss the IV characteristics of solar cell. The IV characteristics of solar cell are basically a graphical representation of the operation of a solar cell or module, summarizing the relationship between the current and the voltage at the existing conditions of the irradiance and the temperature. The IV curves provide the information required to configure a solar system so that it can operate as close to its optimal peak power point, that is called the maximum power point MPP, as possible. The graph here shows the current voltage, that is IV characteristics of a typical silicon photovoltaic solar cell operating under the normal conditions. With the solar cell open circuited, that is not connected to any load, the current will be at its minimum and the voltage across the cell is at its maximum. This voltage is called the open circuit voltage or the VOC. Here at this point the current is 0 or minimum, and at that point the voltage is maximum, that is Vmax. So this voltage is called the open circuit voltage when the solar cell is not connected to any load. At the other extreme point, when the solar cell is short circuited, that is the positive and the negative leads connected together, the voltage across the cell is at its minimum and the current flowing out of the cell reaches its maximum value, that is Vi max. So this current is called the short circuit current or ISC. So this is the VOC, the open circuit voltage, where the current is 0, voltage is maximum. This is the point where the current is maximum and the voltage is 0. Then the span of the solar cell IV characteristics curve ranges from the short circuit current at 0 output volt to the 0 current at the full open circuit VOC. In other words, the maximum voltage available from a cell is at open circuit and the maximum current at closed circuit. The blue line indicates the current curve or the IV curve, and the violet line represents the power curve, that is defined by the VMP multiplied by the IMP, the maximum voltage peak to the maximum current peak. However, there is one particular combination of current and voltage for which the power reaches its maximum value, that is IMP and the VMP. This is the IMP and this is the VMP. In other words, the point at which the cell generates the maximum electrical power, this point, the maximum electrical power, and this is shown at the top right area of the green rectangle. This is the maximum power point. This point is called the maximum power point MPP. Therefore, the identical operation of a photovoltaic cell is defined to be at the maximum power point. This square rectangle is called the maximum power rectangle of the solar cell. It will also have half the RS of the series resistance related to the vertical current flow. However, for large area silicon solar cells, the scaling of the series resistance encountered by the lateral current flow, which is not easily predictable since it will depend crucially on the grid design. Depending on the shunt type, the larger cell may also have the half the shunt resistance RSH because it has twice the area where shunts may occur. On the other hand, if the shunts occur mainly at the perimeter, then the shunt resistance will decrease according to the change in circumference but not the area. Since the changes in the currents are the dominating ones and are balancing to each other, the open circuit voltage is practically the same. The VOC starts to depend on the cell size only if the shunt resistance becomes too low. Now the effect of transparent conducting electrodes on the IV characteristics of solar cell. The transparent conducting electrodes are essential components of the solar cell. It is either a continuous film of the indium tin oxide or a conducting wire network in which the wires are charge collectors while voids between the wires are transparent for light. An optimum density of wire network is essential for the maximum solar cell performance, as higher wire density blocks the light transmittance while lower wire density leads to high recombination losses due to more distance traveled by the charge carriers. Now the effect of cell temperature on the IV characteristics of the solar cell. Temperature affects the characteristics equation in two ways: directly via the temperature in the exponential term, that is T, and indirectly via its effect on the I0. The temperature affects all of the terms, but these two far more significantly than the others. While increasing the T reduces the magnitude of the exponent in the characteristics equation, the value of I0 increases exponentially with T. The net effect is to reduce the open circuit voltage linearly with increasing temperature. The magnitude of this reduction is inversely proportional to the open circuit voltage. That is, cells with higher values of VOC suffer smaller reductions in the voltage with increasing temperature. The magnitude of this reduction is inversely proportional to the VOC. For most the crystalline silicon solar cells, the change in the open circuit voltage with temperature is about 0.50% per degree centigrade, though the rate for the highest efficiency crystalline silicon cell is around 0.35% per degree centigrade. By way of comparison, the rate of amorphous rate for the amorphous silicon solar cells is 0.20% per degree centigrade to 0.30% per degree centigrade, depending on how the solar cell is made. The amount of photoelectric current IL increases slightly with increasing the temperature because of an increase in the number of thermally generated carriers in the cell. This effect is slight, however, about 0.065% per degree centigrade for the crystalline silicon cells and 0.09% for the amorphous silicon cells, that is thin film solar cell. The overall effect of the temperature on cell efficiency can be computed using these factors in combination with the characteristics equation. However, since the change in voltage is much stronger than the change in the current, the overall effect on efficiency tends to be similar to that on the voltage. Most crystalline silicon solar cells decline in efficiency by 0.50% per degree centigrade, and most amorphous cells decline by 0.15 to 0.25% per degree centigrade. The figure shows the IV curves that might typically be seen for the crystalline silicon solar cell at the various temperature. When the temperature increases, the voltage decreases. Now the effect of series resistance on the IV characteristics of solar cell. As the series resistance increases, the voltage drop between the junction voltage and the terminal voltage becomes greater for the same current. The result is that the current controlled portion of the IV curve begins to sag towards the origin, producing a significant decrease in the terminal voltage V and a slight reduction in the short circuit current ISC. Very high values of the RS will also produce a significant reduction in ISC. In these regimes, series resistance dominates and the behavior of the solar cell resembles that of a resistor. These effects are shown for the silicon solar cell in the IV curve displayed in the figure to the right. If the RS increases, the current decreases. Losses caused by the series resistance are in a first approximation given by the P loss is equal to the VRS multiplied by I, that is I square into RS, and increases quadratically with the photocurrent. The series resistance losses are therefore most important at the high illumination intensities. Now come to the effect of the shunt resistance on the IV characteristics of the cell. As the shunt resistance decreases, the current diverted through the shunt resistor increases for a given level of junction voltage. The result is that the voltage controlled portion of the IV curve begins to sag far from the origin, producing a significant decrease in the terminal current I and a slight reduction in the open circuit voltage. Very low values of the shunt resistance will produce a significant reduction in VOC. Much as in the case of a high series resistance, a badly shunted solar cell will take on operating characteristics similar to those of a resistor. These effects are shown for the crystalline solar cell in the IV curves displayed in the figure to the right. When the shunt resistance is increases, the current is slightly increases. Now the effect of the reverse saturation current on the IV characteristics of solar cell. If one assumes the infinite shunt resistance The characteristics equation can be solved for the VOC, where the VOC is equal to the KT by Q ln ISC by I0 plus 1. ISC is the short circuit current and I0 is the minority carrier current or the reverse saturation current. Thus, an increase in I0 produces a reduction in the VOC proportional to the inverse of the logarithm of the increase. This explains mathematically the reason for the reduction in VOC that accompanies increases in temperature, which is already described earlier. The effect of reverse saturation current on the IV curve of a crystalline silicon solar cell are shown in the figure right. Physically, the reverse saturation current is a measure of the leakage of the carriers across the PN junction in the reverse bias. This leakage is a result of the carrier recombination in the neutral regions on either side of the junction. Come to the effect of ideality factor on the IV characteristics of solar cell. The ideality factor, which is also called the emissivity factor, is a fitting parameter that describes how closely the diode's behavior matches that predicted by the theory, which assumes the PN junction of the diode is an infinite plane and no recombination occurs within the space charge region. A perfect match to the theory is indicated when the n is equal to 1. When the recombination in the space charge region dominate other recombination, however the n is equal to 2, the effect of the changing ideality factor independently of all other parameters is shown for a silicon solar cell in the IV curves displayed in the figure to the right. Most of the solar cells, which are quite large compared to the conventional diodes, will approximate an infinite plane and will usually exhibit near the ideal behavior under the standard test condition, that is n is approximately 1. Under the certain operating conditions, however, the device operation may be dominated by the recombination in the space charge region. This is characterized by the significant increase in I0 as well as an increase in the ideality factor to n equal to 2. The latter tends to increase the solar cell output voltage while the former acts to erode it. The net effect, therefore, is a combination of the increase in voltage shown for increasing n in the figure to the right and the decrease in the voltage shown for increasing I0 in the figure. Typically, I0 is the more significant factor and the result is a reduction in voltage. Sometimes the ideality factor is observed to be greater than 2, which is generally attributed to the presence of the Schottky diode or the heterojunction in the solar cell. The presence of a heterojunction offset reduces the collection efficiency of the solar cell and may contribute to low fill factor. Now come to the fill factor of the solar cell. The fill factor is the relationship between the maximum power that the solar cell can actually provide under the normal operating conditions. This fill factor value gives an idea of the quality of the solar cell. The fill factor is defined as the ratio of the maximum power from the solar cell to the product of VOC and the ISC, so that we can write the fill factor is equal to PMP, the maximum power, by the VOC and multiplied by the ISC. So we can write the fill factor is equal to VMP IMP by VOC ISC. Graphically, the fill factor is a measure of the squareness of the solar cell and is also the area of the largest rectangle which will fit in the IV curve. That is the VMP IMP point, this is the IMP point, this is the VMP point. So if we make the square as the VMP IMP, the maximum power, this is the maximum current and this is the maximum voltage, then we will get the square rectangle of a power. It is the measure of the squareness of the solar cell and is also the area of the largest rectangle which will fit in the IV curve. As the fill factor is a measure of the squareness of the IV curve, a solar cell with a higher voltage has a larger possible fill factor since the rounded portion of the IV curve takes up less area. The maximum theoretical fill factor from a solar cell can be determined by differentiating the power from a solar cell with respect to the voltage and finding where this is equal to 0. Now if we put the del IV by del V is equal to 0, then we will get the VMP is equal to VOC minus NKT by Q ln V Q VMP by NKT plus 1. This is the equation of the maximum voltage. The equation above only relates to the VOC, to the VMP, and the extra equations are needed to find the IMP and the fill factor. A more commonly used expression for the fill factor can be determined empirically as VOC minus this VOC, small VOC is defined as the normalized VOC, that is Q by NKT into VOC, open circuit voltage. But this small VOC is called the normalized VOC. So the fill factor is the normalized VOC minus ln VOC plus 0.72 by the small VOC plus 1. So this is the actual fill factor formula which is used to calculate the fill factor of the solar cell. Now go through the reference, then you will get all the notes. Thank you.